Okay, welcome back. This one is going to be about matrix multiplication, and I could probably expand this title a bit to reflect the larger theme of this lecture, which is that matrix multiplication is function composition. More specifically, the composition of linear maps. Those are the functions, of course, that we are concerned with here. Now, what does any of this mean? What is matrix multiplication? In what sense is it function composition? Stay tuned and find out. Okay, well, let's begin with something we know about already, namely boring old function composition. Long ago, you learned that if we have two functions, like f of x is x squared, the squaring function, and g of x is x plus 2, the function that just adds 2 to its input, then these two functions can be composed. In other words, we can form f of g of x, which will be a new function, or g of f of x, which need not be the same thing. For example, in this case, f of g of x is what? Well, we read from the inside out, or from right to left. We start with our input x, and first we run that through the g function, which gives us x plus 2, but that output of the g function is just the input for the f function, the squaring function. So the overall net effect is not x plus 2, but the square of the quantity x plus 2, which we could expand out as x squared plus 4x plus 4. On the other hand, if we compose the two functions in the other way, g of f of x, what do we get? Well, once again, reading right to left, we're going to input x into f, which of course squares it, but then we are taking that output and inputting it into g, which takes what we had before and adds 2 to it. So that's function composition, with which you've been comfortable since presumably pre-calculus or so. One thing to observe is that the results here, f of g of x and g of f of x, are not at all the same thing, which implies that function composition is not commutative. F of g of x and g of f of x are very different. It's not like 3 plus 8 and 8 plus 3. The order matters a lot. I mention this now because we will come back to it in a bit. I am going to show you that matrix multiplication, whatever that is really just function composition, which means that if function composition is not commutative, matrix multiplication will not be commutative either. Unlike ordinary multiplication, 5 times 4 is the same thing as 4 times 5, but when we learn how to multiply two matrices together, if we have a matrix A and a matrix B, then A times B will not in general be the same thing as B times A. It's something that catches people off guard very often, but if you know that matrix multiplication is a kind of function composition, then it's really not surprising at all. Alright, well, instead of composing simple precalculus functions, let's compose some linear maps. In particular, let's let R be the matrix representation of a 30-degree rotation, so R for rotation, about the origin, a counterclockwise rotation, which is always the default assumption in mathematics. You're familiar with that from trigonometry, where we rotate counterclockwise around the unit circle. And let's let F be the matrix representation of a reflection, or a flip, which is why I'm using F, since R is already accounted for, over the horizontal axis. This is clearly another linear map because it is induced simply by reflecting the standard grid over the horizontal axis, which in turn we can accomplish by reflecting the two standard basis vectors over the horizontal axis. One of them, I hat, doesn't move at all, and the other, j hat, does flip across the horizontal axis. Anyway, these are both linear maps. They both have matrix representations, therefore, and what I want to do is to compose these two maps. And naturally, just like our precalculus example, we can compose them in either order. If we have a general vector v in R2, like our general number x in the precalculus examples, well, let's draw such a thing to visualize it. Anyway, if we have a vector v, and we multiply on the left by r, the rotation matrix, then v will get mapped to something like this, rv, by rotating 30 degrees. And then if we take this vector rv and multiply it on the left by F, the flip matrix, then vector RV gets reflected to something like this. Okay, that's one way we could compose those two operations, but the other would be to start with V, our original vector, hit it on the left with F, our flip matrix, which would map it to something like this, and then take this vector, FV, and left multiply it by R, the rotation matrix, which would rotate it 30 degrees to something like this. Well, of course, we can immediately see that the vector F times RV is very different than the vector R times FV. So these two expressions for those vectors are decidedly unequal, which means that even in this context of linear maps, function composition remains noncommutative. The order in which you compose the functions makes a big difference as to the final effect. Now, I want to make an observation about compositions of linear maps. The whole idea of the composition of two functions is that we can think of the composition as a new function in its own right. Like in the precalculus examples, we could think of the function that squares x plus 2 as just a single function. You put any number in and you get out some other number. Well, it's the same thing here with linear maps. If I think of the map that takes any point in R2, rotates it 30 degrees about the origin, and then flips the result over the horizontal axis, I can just think of that as one function. Take any old point, rotate 30 degrees, flip over the axis. So I'm ultimately going from here to here. Similarly, take any old vector, rotate, and flip. So at the end of the day, I'm mapping this vector, V, to this vector, FRV. I don't have to think about the intermediate stages. I can if it's useful, but I can think of the map as occurring all at once, from this vector to this vector, or this point to this point. Now, what would I call such a composite map? I don't mean what proper name, should I call it a rotoflip or something like that? I mean, how would I represent that map as a matrix? Well, there's a fairly natural way to do that. It's the composition of those two smaller maps. So let me just combine them. First, we are doing the rotation, and then we are doing the flip. And note that I am writing the order right to left, just like ordinary function composition, where if we have f of g of x, that means first we do g and then we apply f. In this case, first we do the rotation and then we apply the flip. So FR would be the matrix representation for the composition rotate then flip. The order is very important. Again, we read right to left just like we do with function notation for compositions. And similarly, RF is how we would represent the composite linear map that flips and then rotates, because we're reading right to left. Flip, then rotate. Now we could actually figure out what the matrix FR looks like and what the matrix RF looks like by working out what this composite map FR does to I hat and J hat. Once we know that, those would be the columns of matrix FR. Similarly, RF would be some matrix, some 2x2 matrix, whose columns would be the images of I hat and J hat under this composite linear map, where we flip and then rotate. We could figure out where those standard basis vectors get mapped by RF, and those two vectors would be the columns of matrix RF. Maybe I'll come back and compute one of these two matrices from first principles in a moment, but for now I just want to stick with the notation. Once we've adopted that notation, I could rewrite the two expressions over here. Instead of F times RV, and thinking of it in two pieces like that, I could write that simply as the matrix FR, which is that composite map, times the vector V. And instead of writing this stuff, matrix R times FV, where we apply the flip matrix, then the rotation matrix, I can apply them all at once by rewriting this as matrix RF, which is the matrix of that other composite linear map, a flip then a rotation applied to the vector V. Now FR is some matrix and RF is some other matrix. And this is telling us that they act in different ways on an arbitrary vector V, which is not surprising. They're going to be different matrices because they represent different functions, because composition is not commutative. Now, R is a matrix, F is a matrix, RF is a matrix, and FR is a matrix. And it sure looks like, the way we are writing them, that FR or RF can be understood as the product of F and R. And we will indeed call such things products of F and R. To go from F and R to FR or RF, we will say that is an instance of matrix multiplication, which you know really just means composing the underlying linear maps. But what is remarkable is we will come up with algebraic rules to turn it into honest-to-God multiplication, where we will have written out the actual numbers in the matrix R and the actual numbers in the matrix F, and we'll have some weird rules, and by following those rules we will be able to produce the actual numbers in the matrix FR or the actual numbers in the matrix RF. The rules for carrying out matrix multiplication are kind of complicated. I mean, they're easy once you get used to it, but it looks bizarre if you see it out of nowhere. And unfortunately, a lot of times they're just taught as though they were something handed down to Moses by God on Mount Sinai, and nobody understands what they are or where they came from. If you understand, as I'm trying to convey here, that matrix multiplication is just a way to capture function composition, namely the composition of linear maps, you shouldn't find it very mysterious at all. Anyway, I'm going to build up to those rules from the intuitive geometry rather than just announcing them, leaving you wondering why anybody would define such a thing in the first place. Okay, so maybe we should start working our way towards those algebraic rules for matrix multiplication. And I'm going to begin by computing one of these two matrices with our bare hands, without knowing any rules for matrix multiplication, just so that when we develop those rules, we'll be able to compute it again and say, aha, yes, these weird-looking rules actually did produce what we know it should produce, since we already reasoned our way to that same result, even if we did it in a somewhat longer manner. Okay, so let's figure out what FR actually looks like. So the matrix FR represents the composition of a 30-degree rotation followed by a flip over the horizontal axis. It's going to be a 2x2 matrix because it is a map from R2 to R2. You feed a vector in R2 into this matrix, into this composite map, and it gives you back a vector in R2. As usual, we just have to figure out what this map, what this matrix does to the standard basis vectors in R2, and those will be the columns of this matrix. So let's work that out. Let's start with I hat. What does this map do? First, it rotates by 30 degrees. So it'll take us somewhere around here. Now, to what point does that correspond? Well, that's easy because this is rotating along the unit circle because it started out 1 unit away from the origin. So that point, by basic trigonometry, is cosine of 30 degrees times sine of 30 degrees. And everyone should know, who is taking this class, that sine of 30 degrees is a half, and cosine of 30 degrees, what's that? Well, cosine means sine of the complement. So cosine of 30 degrees is sine of 60 degrees, since 60 is the complement of 30. And again, everyone should know the sine of 60 is root 3 over 2. Okay, that's the effect of just the rotation. But this composite map, this matrix multiplication, not only rotates, but then flips the result over the horizontal axis. So this guy flips to this position. And so, of course, this point and this point have the same x coordinate, root 3 over 2, but their y coordinates are equal and opposite. So instead of half, this one will be minus half. And these coordinates are the components of this vector, which is the image of I hat under this map. So the first column of that matrix is going to be root 3 over 2 minus 1 half. Now, let's move on to the second column, which is the image of j hat. Well, what happens to j hat when you hit it with this composite matrix, FR? Well, it unfolds in stages. We rotate 30 degrees, which brings us here. So what are the coordinates of that point? Well, you could work out, here's 90 degrees, and here's another 30 degrees. Put those together, you get 120 degrees. This is going to be cosine 120, sine 120. Take a minute to figure out what those are and write them down. That's fine. But there's an easier way. We can use the trick that I showed you in the previous video. We've got a right angle right here, and we know the coordinates of this point. So we're just rotating this point 90 degrees. And as I showed you last time, that's very easy to write down. All you do is you swap the positions of the two coordinates and append a negative to the first slot. So this point would have the coordinates minus half root 3 over 2. Okay, but that's just what we get when we rotate j hat by 30 degrees. We still have to reflect across the horizontal axis. When we do that, of course, we reach a point with the same x coordinate as the one we were just looking at, but with the opposite y coordinate. So the y coordinate here will be minus root 3 over 2. No surprise that both coordinates are negative, since we're obviously in the third quadrant. Anyway, these coordinates are the components of this vector, which is the image of j hat under the composite map. So that becomes the second column of FR. Good. So we have worked this out with our bare hands. So if we wanted to know what this composite map FR does to any vector in the plane, this vector, say, we would just get its components, write them down here, do the matrix vector multiplication, and we would have our answer. Now what I want to do is to develop some rules for matrix multiplication, which will allow us to go from R's matrix, which you can confirm is this, and F's matrix, which you should be able to show in seconds, is this, to go from those two matrices to this one by literally carrying out some kind of multiplication that turns these two into that one. So that algebraic project is what we will work on next, and because I'm going to need a fair amount of room, I'll record this information over here so it won't get in the way. Okay, so we are going to develop what I call in the book 2 different algebraic perspectives on matrix multiplication. The first is what I call the column perspective on matrix multiplication, which allows us to think about what the columns of a matrix product should look like. The second is an entry perspective, which will tell us entry by entry what a matrix product should look like. Both are very important. The first is most important for our conceptual understanding. The second is more important for actual computation. We'll need both, and we will begin with the column perspective, which is fairly straightforward. It says that if A and B are matrices that we're going to multiply together, then the product AB looks like this. Okay, I'm not just going to announce the result to you. Let's think our way through it. What is the first column of AB going to look like? Well, AB is the matrix representation of a linear map. What does the first column of such a representation look like? Well, it's the image of the first standard basis vector under this composite map. Okay, what's that going to look like? You might say, well, I don't know. It depends what A and B look like. Like in the case over here, we were able to figure this out because we knew the first one was a rotation of 30 degrees and the second one was a flip. I have no idea what A and B are. Well, that's true, but we do know something about B, which is the first matrix that gets applied in this composition. We know that the first column of B is the image of the first standard basis vector under B. So let's just suppose that B is some matrix, and its first column is some vector that I'll call B1. And while I'm at it, the second column is what we'll call B2, and so on and so forth, up to, say, Bn. Okay, anyway, B1, we said, is the image of the first standard basis vector under the map B. Remember, if we have more than 3 standard basis vectors, we just call them E1, E2, E3, and so on and so forth. Anyway, that's what B1 is. So if we're trying to figure out the first column of AB, we have to figure out what AB does to E1. Well, we know that B, which is the first part to hit it, sends E1 to B1. Then we're going to feed that vector into A. What does A do to B1? Well, I don't know, unless, yes, I know something more about A, but I'm still going to record right here that that first column is going to be A times B1. So this is the image of the first standard basis vector under the composite linear map. The first standard basis vector gets mapped to B1, B1 then gets mapped to A times B1. So that is the net result. Well, what about the second column of matrix AB? Of course, it's going to be the image of the second standard basis vector when it gets hit by matrix AB. But if we think of matrix AB as consisting of these two parts, first do B, then do A, we can figure it out very easily. We take our second standard basis vector, hit it with B, that turns it into the second column of B, which is little b2. That gets hit by A. So the second column of matrix AB is going to be A times B2. And so on and so forth for all the columns. And we now have our column perspective on matrix multiplication. If A and B are matrices, then the product AB looks like this. Every column is A times a column of B. So to write this out, I should add where B sub j is the jth column of B. Let's box up our treasure and move it out of the way. Now, as I said before, the column perspective on matrix multiplication isn't really the one we use when computing specific matrix products, but it's very useful to us as we will be developing the theory of working with matrices. And I'll begin making use of it right away. We're going to use the column perspective to come up with the entry perspective on matrix multiplication, which will tell us that if A and B are matrices, then the ijth entry of AB is, and we'll figure this out in a moment, but by the ijth entry, I mean the entry in row I, starting from the top, and column J, starting from the left. So our job is to figure out what that entry is going to look like. So let's get started. The ijth entry of AB is the entry in row I, column J of the matrix product AB. Hey, wait a second. It's in column J of the product AB. Well, I already know the column perspective on matrix multiplication. What does column J of AB look like? Well, of course, it's going to be A times the jth column of B. So this is equal to the entry in row I of ABJ, which is a column vector, the jth column of AB. And this equal sign comes courtesy of the column perspective on matrix multiplication. So this is a great start because we have already reduced the problem of finding one entry of a potentially vast matrix to finding one entry of a vector. So we've essentially sliced one dimension out of the problem by appealing to this column perspective. So all praise to it. That said, I'm going to need some more room, so I am going to erase it and move everything else upwards. Okay, so now we need to think about this column vector, A times the jth column of matrix B. And this is going to require a little sidebar discussion, so let me rope off a section down here where we can do some dedicated thinking down here in the dungeon, from which we will ultimately emerge with our answer. Okay, so let's think about this column vector A times Bj. A is a matrix, so let me represent that like this, as a series of columns. And I'm calling the columns A1, A2, all the way up to AN. So all that is matrix A. Then I'm multiplying that by a vector, Bj, which looks like, well, some column vector. Its entries are a bunch of numbers. I'll represent them here by various shapes. Why not? A black dot, a square, and so on and so forth, all the way down to a black star at the bottom. Well, this makes me think about the definition of matrix vector multiplication, which we know is a weighted sum of the columns of the matrix, where the weights are drawn from the vector. So this is ultimately equal to something like this. The black dot times the first vector, plus the square times the second vector, so on and so forth, with the last term being the black star times the last column vector in matrix A. And of course, if we had actual numbers filling up all these columns and shapes, we could crunch it all together into one vector, which, as we've said already, would be column J of the product AB. That's where we started from, thanks to the column perspective on matrix multiplication. Okay, now remember where we were back when we were just following our nose. We were trying to find the entry in row I of this vector right here, A times Bj. So for whatever value of I we're looking for, we're just interested in the one row. Now there's only one entry in that row because it is a column vector. So I'll just imagine it here, the entry in row I of column J of AB. What is that going to look like? That is precisely what we're trying to figure out in our entry perspective. And all this weird stuff I've written down back here will help us, because let's think about what is going to appear in that slot. Clearly, what will end up in row I of that column must be the sum of the ith entries of all of these individual terms. So I think it will be helpful if we introduce some symbols for the ith entries of all of these column vectors that appear here. Our first column vector is the first column of matrix A. So I'm going to call its ith entry A sub I1. That's a common sort of notation when working with matrices. The two subscripts refer to the row and column of the entry. So we know the second subscript should be 1 because we're in column 1 of matrix A. And the first subscript will be I because I just want what's in the ith row of that column. Similarly, if we look at the second column vector here, A2, which represents the second column of matrix A, its ith entry will be something that I'll call A sub I2. 2 for the second column, I for the ith row, and so on and so forth until we get to the last column, where I will call the ith entry A sub IN, N for nth column, I for ith row. This strange expression may be making your head spin a little bit with all the weird notation I've introduced with double subscripts and these funny shapes, but we have almost reached our goal, because the goal for the whole thing, to find the ijth entry of AB, which is exactly what will go in this red box here. This is the entry in row I, column J of AB. What can we say about it? This will be the sum of the ith entries of all these terms, so we have to think about what each term contributes. Well, let's start with the first term. We have our column vector, but it's being scaled by this black dot. So every entry in the column vector gets multiplied by the black dot, including this one, the one that's in row I. So I'm not just going to get A sub I1, it's going to be multiplied by the black dot. But then I have to add in what I get from the second term, which is the result of scaling this column vector A2 by the square. So every entry gets multiplied by the square, including the ith one. So my second term here will be not just A sub I2, but A sub I2 multiplied by the number I'm representing with a square, which itself is just the second entry in the vector Bj, which is the jth column of matrix B. There's a lot going on here. But anyway, this will continue all the way down the line until we reach the last term, which contributes what to the ith entry? Well, I think you can see that's going to be A sub IN times the black star. Okay, but how does this help? I hear you cry. Well, you'll see that if you take a step back and recognize this expression as a sum of a bunch of individual terms, n of them, where a particular pattern is playing out. Each term consists of a product of two numbers. Let's start with the second numbers. Those, which I've symbolized by shapes, correspond to the entries in vector Bj. That's kind of interesting. It almost feels a little like a dot product, doesn't it? Where I'm dotting some vector with this vector. But what would the first vector be? Well, go back to those first terms, A sub I1, A sub I2, all the way up to A sub IN. Well, here they are in our earlier work. And remember, these column vectors, those are the columns of matrix A. So if we forgot about all the little shapes and just stuck those columns together, we would reconstruct all of matrix A. So in fact, what we have here, if we just look at those red entries, they're all on row I. So that means they just make up the ith row of matrix A. Well, if that's true, then all I'm doing here is taking that ith row of matrix A and taking a dot product of it with the column vector, which is the jth column of matrix B. So let me write that down. All this stuff is equal to the dot product of the ith row of matrix A and the jth column of matrix B. Well, that's nice. That's something I can actually remember, as opposed to all this crazy stuff that seemed to be going on in the middle of this derivation. What have we learned? We've learned that this entry right here, which we were interested in because it was the entry in row I of the vector ABJ, that thing which we were looking for in our quest for the entry perspective, turns out to be equal to A's ith row dotted with B's jth column. So let me clear out all this junk and record the result back here, where this equals sign is justified by the preceding sidebar discussion. And we've got it. And now that we have attained the ledge we were trying to get up onto, let's condense this even more by throwing away the ladder and just keeping the final result, like so. So the fruit of our labors, the entry perspective on matrix multiplication. If A and B are two matrices, then the ijth entry of AB, meaning the entry in row I, column J, is found simply by taking a dot product of A's ith row and B's jth column. For example, suppose I have these two matrices and I'm going to multiply them together. Now we know each one represents a linear map and we know that their product represents the composition of those two linear maps, where we do the one on the right first and then the one on the left second. And we could figure out that product, as we did over here in our example with the rotation and the flip, by figuring out where that composition of the two linear maps sends I hat and where it sends j hat. And we could try to work that out, whether by thinking geometrically or using the column perspective on matrix multiplication or what have you. But we can also figure it out, and this is what we would do in practice, just by turning the algebraic crank using this entry perspective on matrix multiplication, picking off the new matrix one entry at a time simply by doing some arithmetic. Namely, what's the top left entry of the product going to be? Well, that's first row, first column, entry 1, 1. Well, what we've just learned in the entry perspective is that the first row, first column of the product matrix is the dot product of the first row of the matrix on the left and the first column of the matrix on the right. Well, that's going to be 1 times 5, which is 5, plus 2 times 7, which is 14. Well, 5 and 14 is 19, so that's what we get for that entry. Okay, what about this entry, which occurs in row 1, column 2 of the product? Well, thanks to the entry perspective, we know that is going to be the dot product of row 1 and column 2 of our two respective matrices. Taking their dot product, we get 1 times 6 is 6, plus 2 times 8 is 16, 6 and 16 is 22, and on we go. This entry in the product matrix, that's row 2, column 1. So we get it by taking row 2 of the matrix on the left and dotting it with column 1 on the right. Well, that gives us 3 times 5 is 15, plus 4 times 7, which is 28. Put those together and you get 43. And finally, the last entry appears in row 2, column 2, so we get it by taking the dot product of row 2 on the left matrix, column 2 on the right matrix. 3 times 6 is 18, 4 times 8 is 32. Add those together and you get 50, and our matrix is complete. Easy, isn't it? For our next example, let's return to something we did earlier, where we worked with a rotation matrix and a flip matrix, and we composed them to get the rotation then flip matrix. And we worked all that out by thinking geometrically. Now let's get it just by turning the algebraic crank. If this is F and this is R, then the product FR is the product of those two matrices, and we can crank that product out by doing the multiplication in the usual way, picking it off entry by entry. So let's start in the upper left. That's row 1, column 1. So row 1 of the left matrix dotted with column 1 of the right matrix gives us 1 times root 3 over 2 plus a big fat 0. So that's going to be root 3 over 2. Let's drop down to the bottom left. Row 2, column 1. So we take row 2 of the left matrix and column 1 of the right matrix. Take their dot product and we get minus a half. Let's move to the upper right. That's row 1, column 2. We take row 1 of the left matrix and column 2 of the right one. Their dot product is clearly going to be minus half. And finally, the bottom right entry, row 2, column 2, we get by taking the dot product of row 2 of the left matrix, column 2 of the right matrix, which looks like it will be minus root 3 over 2. And lo and behold, this agrees with what we found by working it all out geometrically, which shouldn't surprise us because it's not like the entry method was something I just made up. We have gone through a derivation to see why it must be true. But now we can come up with matrix products simply by turning a crank. Let's look at a third example. Let's take this 4 by 2 matrix and multiply it by... Wait, can we do that? Yes, we can. And this is actually a good place to stop for a second before we actually carry out the multiplication and talk about how we can tell when a pair of matrices actually can be multiplied. This first matrix is a 4 by 2 matrix. 4 rows, 2 columns. This second matrix is a 2 by 3 matrix. 2 rows, 3 columns. An easy rule, which I'll explain in a second, is that if these inner dimensions match, as they do here, 2 and 2, then we can actually carry out the matrix multiplication. It's very easy to understand why this is so if you bear in mind that matrices represent linear maps and matrix multiplication represents the composition of linear maps. And of course, when we're doing compositions, we go from right to left. And in particular, our matrix on the right, which is a 2 by 3 matrix, represents a linear map from R3 to R2. We take the output of that linear map, which lives in R2, and we run it through the linear map corresponding to the left matrix. Now that's a 4 by 2 matrix, so it corresponds to a map from R2 to R4. The output of the first linear map lives in R2. The input of the second linear map must come from R2. Well, that's exactly what we have. So we're taking a vector from R3, sending it to R2, and then sending that to R4. That's a perfectly valid operation, and it ultimately takes us from R3 to R4. So we should not be surprised that the result will be represented by a 4 by 3 matrix, which again we also see right here. The 2's match, and what's left, the 4 and the 3, give us the dimensions of the product matrix. Anyway, let's work it out quickly, and then I'll come back to this general theme. Okay, starting in the top left, that's row 1, column 1. Here's row 1 of the left matrix, column 1 of the right matrix. 1 times 1 is 1, 0 times minus 1 is 0. So we get a 1 there. Row 1 in the left matrix, column 2 in the right matrix. Dot product is clearly 2. Row 1 in the left matrix, column 3 in the right matrix. Dot product is clearly 3. Row 2 in the left matrix, column 1 in the right matrix. Dot product is 2 minus 5, which is minus 3. Row 2 in the left matrix, column 2 in the right matrix. Dot product is 4 plus 5, which is 9. And so on. I'll let you work the rest out, but they turn out to be these numbers, and we are done with our multiplication. Good. By the way, what would have happened if we tried to do this multiplication with the factors reversed, like this? Would we get the same thing? Not necessarily, because we've talked about matrix multiplication is not commutative, since function composition is not commutative, but it's actually worse than that. This product of matrices is not even defined when we put them in this order. And you can see that by carrying out the same kind of analysis we did before. We'll do just the little shorthand check, but we'll also reason our way through it. The matrix on the left is a 2 by 3 matrix, while the one on the right is a 4 by 2 matrix. Well, as I showed you before, those interior dimensions have to match. They don't here. I've got a 3 and a 4, which means that this product is not even defined. Okay, fine, we see that by following a silly rule, but why does that rule work? It's because each matrix corresponds to a linear map, and their product corresponds to the composition of those maps. Well, to compose two maps, the output of the first one has to be the sort of thing that can be put into the second map. But that doesn't happen here. A 4 by 2 matrix corresponds to a map from R2 to R4. So the outputs of this map are vectors in R4. But those don't fit into the linear map to which the left matrix corresponds, because that linear map eats vectors in R3 and produces vectors in R2. It doesn't know what to do with a vector from R4. So this thing is undefined, which really reinforces the basic point that matrix multiplication is not commutative. Everything can be smooth sailing in one order of the multiplication, and you might not even be able to do the other order at all. And even if you can do both orders, the results need not be the same thing. For example, we had matrix F and matrix R, and we computed FR, but of course we could now very quickly compute matrix RF. And if you do that, you get this matrix, which is not the same thing as FR. In particular, you have a positive entry in the top right in RF and a negative one in FR. And the same thing happens in the bottom left entries. And you might ask, well, is it always the case that if you can do the matrix multiplication both ways, that you get things that are kind of close, maybe only off by negatives in some entries? No, that's not true at all. That just happened here because the matrices corresponded to simple geometric transformations. I'll leave it to you to make up some examples where you multiply two 2 by 2 matrices one way, and then you multiply them another way, and you get results that look nothing like one another. All right, I want to make one more point on this entry perspective on matrix multiplication. It works for matrix vector multiplication too. For example, if I have the telephone matrix, whose rows are 1, 2, 3, 4, 5, 6, and 7, 8, 9, and I multiply on the right by the vector 5, 1, 2, I can, of course, work this out by following the definition of matrix vector multiplication, 5 times the first column plus 1 times the second column plus 2 times the third column, or I can write down the output all at once by using the entry perspective on matrix vector multiplication, which after all really is matrix multiplication. It's just multiplying a 3 by 3 matrix and this column vector, which I can think of as a 3 by 1 matrix. These inner dimensions match, so of course course, the product is defined and is going to be another 3x1 matrix. Well, of course it is. We knew that already. But what is it? Well, the top entry, that's row 1, column 1. Everything is column 1 because there is only one column. But anyway, it's row 1, column 1. So that's just the dot product of row 1 of the matrix and column 1, namely the only column, of the vector. We do that dot product, we get 5 plus 2 plus 6, so we end up with 13. Next, we're in row 2, column 1, which is going to be the dot product of row 2 of the matrix and column 1, namely the only column, of the vector. Do the dot product, and we get 4 times 5 is 20, plus 5 is 25, plus 12 is 37. And to get the bottom entry, row 3, column 1, well, we take row 3 of the matrix and column 1, the only column of the column vector, take their dot product, that's 35 plus 8, which is 43, plus 18, which is 61, and we're done. So this entry perspective gives us a nice, quick way of doing matrix vector multiplication as well. Maybe one more quick example like that is worth doing. Here's a 2x4 matrix and a 4x1 vector. This product is defined. We can see that because those inner dimensions match, but don't lose sight of the more fundamental reason why this is defined. Our definition of matrix vector multiplication tells us that it is a weighted sum of the columns of the matrix, and the weights are the entries in the vector. So we have to have as many entries in the vector as we do columns, which of course we do. We have 4 of each. But let's go ahead and multiply this out, not by using that definition of matrix vector multiplication as a weighted sum of columns, but instead using this entry perspective shortcut, which, as I said, is designed to make computations easy because it just reduces everything down to a bunch of dot products. So let's see. The first entry in the product is the dot product of the first row of the matrix and the column vector. Well, we do that dot product and we get 3 plus 0 plus 10 is 13 plus another 0. So we get 13. And the second entry is the dot product of the second row of the matrix and our column vector. That dot product will be, let's see, minus 6 minus 1 is minus 7, then a couple of zeros. So it will be minus 7, and we've got it. And yes, this only has 2 entries because this 2x4 matrix corresponds to a map from R4 to R2. So that's exactly what it's doing here. It's mapping this vector in R4 to a new vector in R2. So to repeat my endless refrain, don't just get caught up in the rules for computation. Be sure you can jump back and forth between computational methods and ways of thinking about these things geometrically. But from this point forward, you will probably want to do just about all of your matrix vector multiplications using this entry perspective because it's so quick. But don't forget the actual definition of matrix vector multiplication as a weighted sum of the columns of the matrix. Don't forget your roots. Okay, let's think about an example in which I will introduce a very special matrix, which I think has already appeared in the exercises in the book, but I haven't mentioned it here. If I have a square matrix where these diagonal entries on what's usually called the main diagonal of the matrix are all 1, and then all the other entries above and below that main diagonal are all zeros, then this matrix has a special name. It's called the identity matrix, and we typically symbolize it with an I. Anyway, suppose we take our identity matrix and multiply it by a vector. I've just called the entries here A, B, and C because any old vector will do. What does the identity matrix do to the vector? Well, let's think about it in 3 different ways. Let's work our way backwards. Let's start with the entry perspective. What's the product of this identity matrix with vector ABC? Well, it's a vector whose first entry is the dot product of the first row times our column vector. You do the dot product and you get A plus 0 plus 0, so that is A. Similarly, the second entry of the product is the dot product of the second row and the column vector. Their dot product is 0 plus B plus 0, therefore B. And the third entry is the dot product of row 3 with the column vector. That's 0 plus 0 plus C, and our product is done. Oh, interesting. So we take the identity matrix and multiply it by any old vector, and the output is the same as the input, which explains why this is called the identity matrix. It preserves the identity of whatever you put into it. But why does that happen? I mean, we did a bunch of dot products and it worked out that way. Is there a better way to see it? Well, let's think about it again, just using the definition of matrix vector multiplication as a weighted sum of the columns. Then we'd have A copies of the first column, which is I hat, B copies of the second column, which is j hat, and C copies of the third column, which is k hat. We put them all together, and of course we get the same result. Does that help us see better what's going on? Maybe, maybe not. So let's bring things back to geometric bedrock. Geometrically speaking, what does the identity matrix do? It's a 3x3 matrix, so it corresponds to a linear map from R3 to R3. What does that map look like? Well, it's a linear map, a grid transformation. And the transformation of the grid is controlled entirely by the effect of the map on the standard basis vectors, I, j, and k. What does this map do to those three vectors? Well, we can read that off of the columns. I hat gets mapped to I hat. It doesn't move. It's fixed. J hat gets mapped to j hat. It's fixed. And k hat gets mapped to k hat. It's fixed, which means that the identity map fixes all three standard basis vectors, and consequently, the grid does not change at all. So nothing changes. So of course, it's totally obvious that you multiply the identity matrix by a vector and you get back the exact same vector. We don't need to appeal to anything computational to understand this. It's entirely obvious when we think geometrically. The map corresponding to the identity matrix, which we could just call the identity map, is what we might also call the do-nothing map, because it literally does nothing. This can help us understand what happens if we multiply an identity matrix, here I'm looking at the 2x2 identity matrix, by some other matrix as opposed to a vector. What happens then? Well, you could work out the computations, do all the dot products, and that would be fine. But before we do that, let's just think geometrically. This is a matrix product. It therefore corresponds to function composition, to the composition of those two linear maps. And the second linear map does nothing. It's the identity map, the do-nothing map. So what's the composition of this first map, whatever it does, followed by do-nothing? Well, the net effect is just whatever the first map was. So the matrix product, of course, is going to be equal to that matrix on the right. So be sure you understand why that is so geometrically, rather than just saying, well, all right, I'll do the dot product. That's A, so I get here, and then I have to do that one, and that's B. I mean, that second way is fine too, but it doesn't actually show you what's going on. Oh, while we're talking about this sort of thing, what happens if we were to reverse the order of that matrix multiplication? Does that change the result? I mean, we know matrix multiplication is noncommutative, so we have to be careful. Well, in this case, the result does work out to be the same thing. And again, just think about it geometrically. When we're looking at a composition, we read from right to left, just like function notation. What do the two parts of this composite function do? Well, first we take whatever the input is and hit it with the identity matrix. Well, that doesn't do anything to it. It doesn't change it at all. And then we hit it with this other matrix. So the total effect, the net effect, is just whatever effect the second matrix had. So of course, the product is the matrix on the left. And once again, we see the virtue of the name identity matrix. So even though matrix multiplication is noncommutative in general, there are specific cases in which you can multiply two matrices in either order and you get the same result. I mean, that's not too surprising because function composition is the same way. In general, it's non-commutative, but there are certain functions that you can compose either way and you get the same thing, like the doubling function and the tripling function. Whether you double and then triple or triple and then double, doesn't matter. The result is 6 times whatever the input you started with was. All right, enough already about the identity matrix. You've now seen what matrix multiplication is, and you have seen that matrix multiplication is function composition. More specifically, linear map composition. Two sides of the same coin. An algebraic side, a geometric side. And each side gives us insight into the other. The fact that I have been reduced to mere doodling on the board suggests that we are more or less at an end, which is true, although there is one last thing I should mention. We can not only multiply matrices, we can add matrices too, but it's not very exciting to do so. You can only add matrices of the same size, like these 3x2 matrices, and you add them just by adding the corresponding entries. So there's a 1 and a 7 in the top left entry, so we add them and get 8. For the sum. We can do the same thing in all the other positions, and we end up with something like this. Okay, so computationally it's trivial. What's going on geometrically with the addition of matrices? Frankly, not a whole lot, so I don't have that much to say about it here. Please do read the little section on matrix addition, which includes some exercises which demonstrate a nice application of matrix operations, including addition, to the manipulation of images on a computer, specifically pixelated images. It's a nice application because it involves gigantic matrices, so it's another opportunity to think about things like that. But there's no deep underlying geometric significance to matrix addition. It's mostly the sort of thing that we define because it makes our lives a little easier in certain cases. There's another operation on matrices that I introduce in the same section called matrix transposition, and that is something you do to a single matrix. For example, if I have this 3x2 matrix, I can transpose it. I symbolize that by putting a little t, kind of like an exponent, on the matrix, and all the transpose is an operation where we swap the rows and columns. So the first column of the original matrix becomes the first row of the transposed matrix. Similarly, the second column becomes the second row. So instead of having a 3x2 matrix, now we have a 2x3 matrix. As we'll see, this is an occasionally useful thing to do. And that brings us to the end of the videos for Chapter 3. So I will see you next time as we move on into Chapter 4, where you will finally learn how to solve systems of linear equations by Gaussian elimination. Until then, goodbye.